Hello and welcome to this session, LO3. Apply Le Chatelier's principle to explain how changes in conditions affect a system in dynamic equilibrium. Today, we will explore how equilibrium systems respond to external changes and how Le Chatelier's principle can be used to predict the direction of shift in chemical reactions. Dynamic equilibrium occurs when forward and reverse reactions happen at the same rate. Concentrations remain constant, though not equal. The system appears unchanged, but reactions continue. A closed system is necessary for equilibrium. No substances enter or leave, allowing equilibrium to establish. Le Chatelier's principle states that a disturbed equilibrium system shifts to oppose the change. This restores equilibrium by adjusting the reaction direction. It applies to concentration, pressure, and temperature changes. Understanding this principle helps predict system behavior. It's essential for explaining chemical reactions. Increasing reactant concentration shifts equilibrium to the right. This uses up the added reactant. Increasing product concentration shifts equilibrium left. The system compensates by reducing the product amount. Removing substances causes a shift to replace what was lost. Pressure changes affect gaseous equilibria. Increasing pressure shifts equilibrium to the side with fewer gas moles. Decreasing pressure shifts to the side with more gas moles. This adjustment balances the pressure change. It's crucial for reactions involving gases. Temperature affects both equilibrium position and reaction rate. For exothermic reactions, increasing temperature shifts equilibrium left. For endothermic reactions, it shifts right. Decreasing temperature has the opposite effect. This understanding helps optimize reaction conditions. A catalyst speeds up both forward and reverse reactions equally. It doesn't change the equilibrium position. However, it helps the system reach equilibrium faster. Catalysts are crucial in industrial processes. They improve efficiency without altering reaction balance. Students should draw diagrams showing concentration versus time, annotate direction of shifts, and causes of disturbances. Diagrams support explanations and calculations. Visual aids enhance understanding of equilibrium changes. They are vital tools in chemistry education. The Haber process synthesizes ammonia from nitrogen and hydrogen. It's an exothermic reaction, releasing heat. High pressure favors ammonia production by shifting equilibrium right. Low temperature also favors production but slows the reaction. Industrial conditions require a compromise. In the Haber process, high pressure shifts equilibrium to the right. This side has fewer gas moles, favoring ammonia production. However, high pressure is costly and risky. A balance is needed between yield and safety. This demonstrates industrial application of equilibrium principles. Low temperature favors ammonia production in the Haber process. However, it slows the reaction rate significantly. A compromised temperature of about 450 degrees Celsius is used. This balances reaction speed and yield. It illustrates the practical application of equilibrium knowledge. Industrial processes require a balance between rate, yield, and cost. The Haber process exemplifies this compromise. Conditions are optimized for efficient ammonia production. Le Chatelier's principle guides these adjustments. It ensures economic viability while maximizing output. By mastering LO3, students define dynamic equilibrium and closed systems. They apply Le Chatelier's principle to predict shifts. They explain effects of concentration, pressure, and temperature. They interpret and draw equilibrium diagrams. They explain industrial optimization using the Haber process. Consider the Haber process for ammonia synthesis. Increasing pressure shifts equilibrium right, producing more ammonia. Increasing temperature shifts it left, reducing yield. A catalyst speeds up the reaction without shifting equilibrium. This example highlights the principle's practical application. Le Chatelier's principle predicts equilibrium system responses to changes. It applies to concentration, pressure, and temperature variations. The system adjusts to counteract changes and restore balance. Understanding this principle aids in optimizing chemical reactions. It's a cornerstone of physical chemistry. Refer to ebooks and journals for deeper insights. Additional resources are available on the Moodle platform. For queries, contact LearnerWork at UKversity. Assignment submissions are due 2 weeks post-unit completion. Continuous learning enhances your chemistry understanding. This is the conclusion of the video. Le Chatelier's principle is vital for understanding equilibrium. It explains how systems adjust to maintain balance. This knowledge is crucial for both academic and industrial applications. For any questions or further information, you can reach us on WhatsApp at 0748-436-1688. Thank you for listening, and see you at the next session.